So this next screencast is intended to show you how to take a second integral and go from a velocity as a function of time formula to a position as a function of time. Just as a kind of foundation for integrals and derivatives. If you're taking derivatives, x prime of t equals v of t, and v prime of t equals a of t. The prime you could also write it as dx dt equals v, and you could write this other one here as dv dt equals a for the instantaneous velocity and the instantaneous acceleration. Okay, let me just erase this. Okay, so what I already had shown you was that after taking an integral of acceleration as a function of time, we got the velocity formula, v of t equals v initial plus at. Okay, so now what we want to do is, using this and some more calculus, we want to get to a position formula, x of t, if something's accelerating with a constant acceleration, as in its speed is going up by the same amount each second. Okay, so what we can do is write v average equals delta x over delta t, where delta x is your displacement, delta t is the time interval that you've been displacing yourself for. However, we're more interested in calculus notation and not finding averages, but instantaneous values. So if I were to write v in differential form, I would write v equals the limit as delta t goes to 0 of delta x over delta t, and that equals dx dt. Okay, so let's just write it again. The result there is v equals dx dt. This is an instantaneous value for v as long as you know x of t. But we don't know x of t. That's the whole point. We're trying to find out what x of t is, so we have to do the opposite of a derivative, which is an integral. So if I separate these variables out, I end up with dx equals v dt. And since the object is accelerating and its velocity is increasing each second, this v here is not a constant. So I can't factor it out of my integral here on the right side. And the position x is certainly not a constant because it's moving, and it's not only moving, it's speeding up each second, so we have to integrate both sides. So what we end up with here is x equals, well, now we have to ask ourselves, do we know what v is as a function of time? Because we're integrating v of t. And from the last part the last screencast I had done, we had shown that v as a function of time is v initial plus at. So all I've done is substituted in for v of t the equation for the velocity as a function of time. And now we're integrating this right side, dt. I'm just following along with what's over here. I just substituted in v initial plus at for v of t. So now I have x, which is its position. Could be y if this was something that was falling vertically. X's could all be y's here. I guess I'm using x's to assume that something's moving horizontally. So now we have x equals v initial dt, because we really have two terms here, one over here and one over here, and they both have to be integrated with respect to dt. So I can separate those out as v initial dt plus at dt. And these are integrals now. So now I have x, the position as a function of time, equals Well, this v initial is just a constant number. It's your initial velocity at 0 seconds. So I can factor that out of this integral here. And so I end up with v initial integral of dt plus, and we've assumed that this is a situation where you're accelerating with a constant value. Your speed's going up by the same amount each second, like in free fall. So a here is a constant, so I can factor that out of this integral. I can pull a out. So I can write plus a, and now I'm integrating t dt. Oops, sorry, that's not supposed to be t squared. So now I got t dt. Now when I do this integral, I end up with x as a function of time equals, so when I do this integral over here, I end up with v initial t plus, and now when I do this integral over here, I get a times t squared over 2, but t squared over 2 is the same thing as writing it as 1/2 at squared. Now I have to add a constant of integration, c. So the constant of integration, this here, c, is always just the initial value at 0 seconds. So I could write, let me just erase some of the this top area to give myself some more room. Okay, so now we have, down here, we have a constant of integration to deal with here. X of t equals v initial t plus 1/2 at squared plus c. So the question is, well, what is that c? C is the value when the time value is 0. So x of 0 is always your initial value. What was your position at 0 seconds? Is whatever your value was at 0 seconds. You call that the initial value. So if I evaluate this whole equation at x equals 0 seconds, I end up with x of 0 equals v initial times 0 plus a times 0 squared over 2 plus c. And you can see these all zero out, and you end up with x of 0 equals c. But we already knew x of 0 equaled x initial. So all you've really shown and proven is that the initial c equals the initial position. So when you substitute that in down here for c and rewrite this exact same equation, you end up with x of t. I'll write the constant value first. C here is now just x initial, so I write x initial. I'll write this term right here next, so I have plus v initial times t. And then I write this term right here last, so I get plus 1/2 a. This is really the acceleration along the x direction, because this is an x equation, t squared. And that's the position formula for accelerated motion. You could use that for, horizontal motion. If something was sitting on a flat surface and something was pushing on it with a constant force, then it would have a constant acceleration. Like if you're sitting in a chair with wheels on it and I push you down the hallway and I push on you with a constant force, then you're going to accelerate with a constant value. Your speed's going to go up by the same amount each second. And if I want to know what your position x as a function of time is, I just need to know where did you start, x initial, what was your initial velocity. This is really the initial and the x, that would be 0, that this term here would cancel away, and I got the 1/2 at squared. If it was a vertical situation where something is just falling, you drop a pencil or a penny and it's falling vertically, these x's here would just become y's. It would be y of t equals y initial plus your initial velocity in the y direction plus 1/2 a. This would become a in the y, which we know is just g, acceleration due to gravity, t squared. And that's it. That's the position formula that you guys had been familiar with from last year. And I've now shown you how to derive that using calculus. All right, bye.